for a galvanic cell that consists of gold, the gold 3, gold 0 half cell or half redox couple, as we say sometimes, and the nickel 2 plus nickel 0 redox couple. Okay, so we could go to the table, so I'm not going to pull up the table, but we've talked about the electrochemical series in a fair amount of detail. We'd go to the table and we'd look for those, and what you'd find in that table, and I'm just going to sort of begin to write this out. Gold 3 plus 3 electrons is going to go to gold 0. Okay, and the E0 for this, if you look in that table, is, I'm going to shorten it a little bit, it's nominally 1.5 volts. Okay, all right, that's the gold one, and then the nickel one would be what? Nickel 2 plus 2 electrons. It's going to nickel, metal, and its E0 is equal to minus 0.257. I should have rounded that to 2.26 for consistency. I apologize for not doing that. Okay, so we can write the complete reaction for that. First, let me ask you guys, what is what's going to be oxidizing what in this example? What's the oxidant?
We will have to flip nickel and it will be oxidized.
That's exactly right. So the oxidant therefore is going to be the gold 3, right? That's essentially what you said, Elizabeth. And the other thing too is we're gonna have to do that, right? So our delta E, our delta E0, if you will, is equal to the E0, and I'm just going to abbreviate gold, the gold couple, right, minus the E0 for the nickel couple, right? So that equals 1.5 volts minus, and this is one thing I will occasionally miss, we all do, and it's a watch out. You got to remember your signs, minus a negative 0.25, I'm going to say 26 volts. Okay, and that comes out, if you do that math, about 1.76 volts. All right. So
sorry, I was in the waiting room, so I never was like added. So just a question, how did you get like the E? Like how did you get 1.5 volts and negative 0.2?
Yes, thank you for that, Connor. The way we got that is by looking at our table. And I am not showing the table, okay? I'm not showing the table. So, but you remember the electrochemical, the table of the electrochemical series?
No.
Okay, all right. Well, let me see. We'll just go back and take a quick look. Let's do that. Let me see if I can find. Let me go back. Let me go back here. Let me end the show, and we'll come back to that example in just a second. Let me first clear that. Clear my drawings. Okay. Let me make that bigger. Can you see that?
Yes, sir.
Okay, so the gold 3 was up there at the top.
Okay.
1.498 volts, right? And that's the oxidant because it's got a very large positive E sub 0, or E with the superscript 0, very large standard potential. And the nickel, therefore, is going to be the one that gets reduced, as Elizabeth said, And that one is somewhere down here, I think, way down there. Yeah, minus 0.257.
Gotcha. Okay.
So if the ACS test, has a question like this, then absolutely they will provide the relevant table, or it may not be a table, but they will provide the data in some way. Okay, so that you'll be able
Thank
to pull
you.
it right out. Yes, absolutely. Good question. No, and I did not show that just because, yeah, that there's, well, I got precious real estate on my little screen here, but let me go back to that. And now let me just reiterate one thing here before we leave this example, and that is so the delta E that we calculated, and you'll also see that sometimes written as like an E cell. It's a cell potential, CELL. It may have a 0 there if it's under standard conditions, and again, that's equal to, another way to think about this, E0 cathode minus E0 anode. Okay. Now, what always happens at the cathode? Reduction.
Is that the oxidation or the reduction?
That's the reduction, okay? But remember, the oxidant, the potent guy, right, the one high up on the table, is being reduced. So that is a reduction.
Gotcha.
And the anode is oxidation. Okay. So E cathode minus E anode, and that is for a galvanic cell. And we touched on this. I think I may have asked one question. Can you make a cathode an anode? So can we cause the opposite to occur?
Yes, but it would be electrolysis and there would have to be an input of energy.
That's exactly right. That would be an electrolysis, and you would need an energy supply in order to do that. Okay, so that's exactly right. You can, instead of having a galvanic reaction, you could create what we term electrolysis, which is just something where we apply the energy to the system. But we can make a cathode and anode by doing that. Normally, for what we call a galvanic cell, the cathode is going to be the cell that will be doing the cathode. The reduction of the potent oxidant is occurring at the cathode in a galvanic cell without our intervention. Very good, thank you. Good review. Now let's talk a little bit about the Nernst equation. If I don't do anything else today, I want to make sure that I've exposed you guys to the Nernst equation. It's fundamental to electrochemistry, and it's fundamental to thermodynamics, and we're going to tie them together. We're going to tie all this stuff together. So let's do that. Let's start with a little bit of a derivation, okay? And we can start by thinking again just about delta E. So we've got two couples, two redox couples, and that's equal to E0 reduction or cathode minus E0 oxidation or anode, right? And that's sometimes just referred to as E0, but there's always two. Remember, you need two electrodes. So there's always, just kind of keep in mind, there's always a difference between two things going on there, okay? Now, I'm going to give you a very important fundamental relationship. Delta G relates to E. Delta G linearly relates to that delta E that we just wrote above it. Okay, it linearly relates to it. It's got a couple of terms in front of it. But the first thing I want to do to kind of to take you a minute to sink in is the relationship, the direct relationship or the linear relationship between delta G and E. Now, I have a question for you. We remember spontaneous versus non-spontaneous reactions, right? If spontaneous, and I'm just going to write, if spontaneous, then delta G has what kind of sign?
Negative.
Less, well, I said less than 1. Yes, Nathaniel, thank you. It absolutely is less than 0. And if it's non-spontaneous, delta G, of course, is greater than 0. And if it's at equilibrium, what is delta G?
There.
Absolutely. Awesome. All right. Now, if delta G, now I would like to ask you, if you recall, if delta E is positive, is a positive delta E consistent with a downhill or spontaneous reaction?
Yeah.
So therefore, that's right. So therefore, the relationship between delta G and delta E has to have a negative sign, right? It's got to have a negative sign associated with it. And to make this thing exact, we've got two terms here called two constants. Well, no, one of them is a constant. Delta G is equal to NFE0, okay? So delta G is equal to NFE0, and that is a very important relationship. Okay, now N is going to be equal to the number of electrons transferred. So in other words, when you get, you know, as we had in our, that may be off the screen, in our previous example, gold 3 accepted 3 electrons, right? So you would need to factor that in as N when working through these relationships. Just keep that in mind. It comes straight out of the tables. It's not magic or anything, but it does require that you take care of those things. Okay, so that's one piece of information. The other is F. Okay, and F is what we refer to as the Faraday constant. And we talked about this when we talked about a type of electrolysis referred to called coulometry, where we were able to quantitatively relate the current, or more specifically, the charge, current times time, to the number of moles of substance that is being electrolyzed. And that Faraday constant is also something, of course, that in any sort of test you would be given it for reference, but I will just let you know now. I don't have it written in front of me, but it's 96,400 and roughly 85. Sometimes you see it 90, sometimes 87, and it's coulombs per mole. Okay, all right. So, you know, in other words, coulombs per mole, that's the units of Faraday. N is the number of moles of electrons, okay? That will give you a unit of voltage times coulombs. Volt coulombs, VC, volt coulombs, okay? And a volt coulomb is related to a joule, kilocalorie per mole, you know, that type of thing. So in other words, we're talking about energy here. Okay, that's all we're talking about, energy, and those units tell you that. As long as you remember that a volt coulomb Dc is related to, it is essentially an energy term, okay? All right, give me a minute, just let me continue down this list here, and I'm gonna get rid of this for a minute. Everybody following this so far?
Yes, except n, the number of transferred electrons. If we
Yes.
look at the reaction, gold did transfer 3 electrons, but nickel transferred 2. So if we were to completely balance that equation, the number of transferred electrons would actually be 6. Would we then use that, or do we just use it for specific substances?
I'll tell you what, I think we're going to work an example on that in just a minute, Elizabeth. So just stay tuned on that answer and we'll work through it and we'll see what precipitates out, okay?
Okay.
That's a great question. Thank you for that. That's a very, very insightful question. All right, so let's finish this derivation here, delta G. Now I'm going to share with you something else that we have is equal to delta G0 plus RT log. And does anyone remember what we put inside there? Let me give you a hint. In this case, that's very, very, you're right on track. The only thing is since we are, the delta, fact that delta G here equates to delta G0 means that we're not necessarily at equilibrium here.
Okay.
So yeah, so in that case, the more generic form of that is Q, right? Yeah, but yes, it's a constant, or the equilibrium type constant setup. Absolutely. All right, so that is from thermodynamics and from the free energy discussions that we've had in the past. All right, let's keep on going down with this thing here. Now, delta G, and we know delta G's, well, I'm going to tell you actually, I'm going to say delta G0 is equal to NFE0. All right, that's really what I should have said with a minus sign. So let's do minus, and delta G is equal to minus NFE. So we could put delta G or NFE minus NFE. See, I almost forgot my minus sign. We got to be real careful. Is equal to minus NFE0 plus RT log Q. Okay. And by dividing both sides, okay, everywhere, I'm going to divide this NF away, and I'm going to divide by minus NF. So if you think about it, that's going to leave E, is it not, is equal to E0, and that plus is going to go to a minus RT over NF L N Q. All right. That is the next important equation, okay? And that is what we refer to, or that is a rendering of the Nernst equation. So in other words, the Nernst equation relates the cell potential, E or delta E. Remember, everything is really a delta E, but it relates the cell potential to this term Q, right? And remember Q, just let's get in a very generic sense, A plus B is going to, you know, and it's in equilibrium often, C plus D. Sometimes it's very, very far to the right, sometimes very, very far to the left, but Q is equal to C D over concentration of A, B. Okay? So the Nernst equation relates the potential of a cell to Q, which is a concentration, effectively a concentration term. All right, now we're not finished because we got one other thing I want to do. Now I'm going to just give me just one other moment here. I got my kind of precious real estate, so I'm going to get rid of some of this stuff that we've now talked about and just focus on this last equation for just a minute. Get rid of all this stuff. Takes me a second. My eraser is not as big as I would like for it to be. All right. Now, if we and now I'm gonna kind of jump to an answer here. At equilibrium, E is equal to, lo and behold, 0, right? And that means Q has gone to K, okay? So 0, just plug in 0 here, is equal to E0 minus RT over NF Ln, and now Q becomes KEQ. Okay. All right. So, and let me erase. Hate to erase stuff, but I got to have some real estate here. So E0 is equal to RT over NF Ln KEQ. So that is the relationship. That's another important relationship. So if you calculate a delta E0 for between two redox couples, you can also, by manipulating this equation, calculate the equilibrium constant. So yet another way, using electrochemistry to get to an equilibrium constant by very simply measuring voltage. Okay. Now, do all reactions have? Can you put anything and everything in an electrode cell and get a voltage? No, can't do that, right? So it's because some things don't pass electrons into an electrode. At least they all pass electrons one way or the other if you're going to do chemistry, chemical synthesis through bonding and whatnot, but you don't always get electrons transferred directly to electrode surface. And what I mean by that, just say for example, you take some gasoline, you put your gasoline in your electrochemical cell. Now is that gasoline, is that octane going to transfer electrons to that electrochemical cell? No, it's not. Of course, it's just not electroactive. It's not going to do anything. It doesn't want any electrons, and it's definitely not going to give up any electrons. So not everything is electroactive, certainly, but for those things that are, this is an extremely powerful relationship. And I'm going to go I'm going to do a couple of other manipulations here too, because we're going to get to a point at which, let me erase this. So the other thing too about this guy RT over NF, that's essentially okay. I'm gonna go up here. You can plug in for standard conditions. So for standard conditions, T is equal to 298. Okay, 298K. Right. That's T. And the other thing about a natural log is ln of x, and this is something that is on the log sheet. Ln of x is equal to 2.303 log of x, and this log being is the base 10 log. Okay, So, and the reason I'm doing this is because the term, what I'm getting ready to show you, is a very common manifestation of the Nernst equation, okay? If you do that, then you get, let's see, E0 is equal to 0.059 over N log, base 10 log of K EQ, okay? It's another way to think about the Nernst equation using the base 10 log. And people like to use base 10 logs because if you get things to a base 10, then you can look at, of course, the exponent and sort of get a real sense of what the number means very quickly. Whereas a natural log term is, it's less intuitive, but a base 10 log is more intuitive. I think that's why you see that happening. So let's do another manipulation here. Okay, let's see if I got, I believe yeah, that's right. So now let's kind of rearrange this log of K EQ is equal to N E0 over 0.059 volts. Okay. So KEQ, therefore, is equal to 10. Got that written down somewhere. I can't find it. I'm looking for it. It doesn't matter. 10 to the raised to the power of NE0 divided by 0.059. So it's just manipulating. And so what I did there is I raised both sides to the 10, power of 10, right? So I got the log, I removed the log from the left side, and I basically put 10 over there, right? So I raised both sides to the power of 10, and that's the equation that I get. Okay. So that's yet another rendering, if you will, of how K and E0 relate, okay? But not to get too wrapped up in the different manipulations, just remember E0 is equal to RT over NF log K, which is also equal to 0.0, it's a horrible 0.059 volts over N log K. And I made one boo-boo. I can see it right now. That was natural log. And this is base 10 log. Okay? All right, so that's the Nernst equation. Another rendering of the Nernst equation, okay? All right. Okay, so far so good. Clean that off.
I have a question.
Yeah.
Is there any way you can mute the person who has their alarm clock going off?
Oh, there's an alarm in the
I'm sorry,
background.
but it's driving me. Yeah, it's driving me crazy.
It's driving me insane too.
Okay, yes, funny. I did not even hear it. It's just an issue. I guess my end is not as sensitive. Yeah, let me see if I can find that. Okay, I can do I don't want to mute everybody, certainly, goodness. Let me first ask, does anyone on the screen, real quick, anyone in the audience, can you please mute your alarm clock, please? Not gonna work, is it? All right, well, in that case, I'm gonna go ahead have to do a mute here. Let me check. And then you can unmute yourself when you, if you want to, okay? But I'm gonna mute everyone. All right. And someone just give me a thumbs up. Did that quiet things down a bit? Okay, good.
Yes,
Thank you.
thank you.
Yeah, got it. Awesome. I appreciate that. I honestly did not even hear it. That's wild. Okay, I have to think about that. Okay, so now moving right along, and we're recording this, of course. And now that we're going to summarize some stuff, if delta G is negative, it's spontaneous. If it's greater than 1, it's spontaneous. E is positive, okay, spontaneous. So if E cell is negative, then it's not spontaneous. This is a triangle too, which I think is useful, kind of summarize what we just talked about. And you know, this is just a three-legged triangle, so to speak. And it shows how delta G, E0, and K are related, and they're all related. They're all thermodynamic quantities, and they're interrelated from one to the other. And delta G is minus RT log K. Delta G is minus NFE cell, right? So minus NFE cell, you can just plug the two. You can plug. You can kind of use these two legs, right? You can plug this guy right into there, and you get this thing. E cell is proportional to K without the minus sign, and that's how it drops out. Okay, so it's kind of a useful construction there. Help keep things together. Just talking about thermodynamics. All right, let's see what else is going on here. I think we've talked about, okay, I did want to talk a little bit more about the Faraday constant. So the Faraday constant is the amount of charge in a mole of electrons, a whole mole, okay? And the derivation is in your book, but it's kind of neat to know that you can derive, this is the number of moles. I mean, this is the charge, I'm sorry, that's Avogadro's number, right? That's Avogadro's number. Okay, this is the coulombs on a unit electron. Okay, they multiply the two together to get the Faraday constant. Okay, and they and notice here is in coulombs per mole, but you can convert coulombs, right? A volt coulomb is equal to a joule.
Okay.
Definitely directly related to energy. Okay.
Mhm.
Yeah. Okay, so thought that was kind of cool. Now let's erase that, and then
Okay.
go on here. Use F, the number of electrons surrounding, and the use cell to get the free energy of the cell. So we've talked about that several times now. All right, and we've talked about these relationships. It's just another rendering of it, and this is the base 10 log between K and E0 cell. What is the standard free energy change and the equilibrium constant for the following reaction at 25C? Okay, well, let's look into this, and let's see if this helps us with that question that Elizabeth asked some time ago. So when I see a problem like this, the first thing that, or when we see a problem like this, the first thing we're going to want to do is kind of break it down. Always make things a little simpler. That way you can see it better. It's like, I'm seeing a forest, but I need to see some trees initially. So the anode, or the oxidation, you can just refer to that. What's that? What's going on here? So Fe is equal to Fe2 plus 2 electrons. The cathode is Ag plus 1 electron is going to Ag0. Okay.
Do you mind explaining why you chose what as the anode and the cathode?
I don't mind at all. And what I would do, and I appreciate you again asking me that. So when you're given a problem like this, the first thing I would do is pull that table up. That's
Gotcha.
that's the holy grail, right? And that table is going to show you that the silver couple, okay, the silver couple has an E0 that is more positive than the iron couple, okay? So I know that silver ion is going to oxidize iron, okay? I know that's going to happen. The other thing too, how's it written? Often the hints right there in how they write it. Most of the time, these textbooks and these problems are going to write things where the right is in the, the downhill direction, right? The going to the right is the forward or thermodynamically spontaneous direction. So if that's the case, then you're going to start out, you're going to take silver plus and go to 0. All right. So there's really, I guess there's 2 answers to that, Connor, and you can use whichever one you have available to you to get to that answer. Does that help?
Yes, thank you.
All right. Yeah. And this E is, let me see if I got my E. Okay. Again, it's, and I'm around. I like the round. Sometimes you get significant figures issues, and I don't, you guys know significant figures, so I might get dinged on this answer, but I'm just going to round the E0 to 0.8 there. And that's the E0 for the silver, Ag, and the E0 for the iron is equal to minus 0.45. Yeah, roughly. Okay. So E0 is 0.8 and then a minus 0.45 for the cathode and the anode, respectively. And again, our E cell, and sometimes you'll see it written E0 cell, again, or delta E, as equal to E0 cathode minus E0 anode. Okay. Now let's see, I believe I have already, let's see, so there's one thing we need to do here, all right? And we're going to get into balancing in just a minute. 9:30, we've got about 30 minutes, so I think we're going to be able to do balancing. But, there's 1 electron here, but there's 2 electrons here. And in order to come up with this equation, and they've done it, you have to multiply this guy by 2. Okay. Now, do we multiply the E's? See if you remember from last time. By
No.
2. We do not. That's exactly right. We do not. A potential is a intensive, I think they call it, versus extensive property. In other words, voltage is not related to quantity of stuff. It's related. It's like measuring temperature, right? It's a measurement phenomena, and the more or less you have is not going to affect the voltage. You can play around, of course, with and we talked about this. Nathaniel brought this up at the last time. You can gang together cells and build voltage, but within each cell, you can't change the thermodynamic voltage. You just can't do it. You can add a whole lot. You can make it bigger and do whatever you want to, and you cannot change the thermodynamic voltage. Okay, you tweak it with concentrations, and we may have an example on that. But you don't multiply those terms. Okay, so E0 cathode minus E0 anode, and this is going to be roughly 0.8 minus 0.45. Okay, so it's 0, and I'm gonna say 0.08 minus, and again, I believe the iron is negative. Yes, minus, you got to watch that because it will bite you. 45 minus 0.45, which is equal to roughly 1.25 volts. Okay. All right. So that's a galvanic cell as written, and it has a voltage. Cell voltage is 1.25 volts. All right. Now, what would we do in order to? What was the question? Let's go back to the question. What is the standard free energy change and equilibrium constant? Okay. So delta E cell we just calculated. All right. So we also know that E cell is equal to E cell is equal to 0.059 over N log, well, not cog. My brain and my hand are often disconnected from each other, so sometimes my hand just scribbles and my brain is trying to tell it not to. 0.059 over N log K. All right, so K is equal to 10. Again, I'm just moving things around a little like but I showed you on the previous screen. K is equal to 10, and that 10 is raised to the power of N times our E cell, E0, I'm just going to call it E0, and then that is divided by 0.059, okay? 10 to the 0, 0.059. Now what's N here? N is going to be 2. It's going to be 2 because we're getting 2 electrons here out of this, and we're making 2 form here, right? So that 1 really is 2 because we multiplied it, okay? So that's equal to, and that's K, 1 point, this is a huge number, 1.3 times 10 to the power of 42, okay? So let's think about K here for a minute. Does that mean that that reaction is favored as written? Well, let's ask. Well, I think you know, but I'm just.
Yeah.
Let's just go. Yeah, you guys know. Let's go ahead and.
Dr.
Yes, go
Jernigan?
ahead. Yes, sir.
So did you do 10 to the 2 times 1.25 divided by 0.059?
Yes, sir. Oh shoot, that's exactly what I did. That was 10, and that 10 was raised to the power of 2 times all of that quantity there, which is 2 times delta E cell or E cell divided by 0.059. That's exactly what I did. Okay.
Okay, well, maybe I messed up. I came up with something different, so.
Oh, did you? Okay.
I had maybe like, I don't know what happened.
Well, did you get a large positive number? Let me ask you that.
Yeah, it was still 10 to the 42, but it was like 2.3 times 10 to the 42.
Well, I'll tell you what, I think here's what I've done. I've rounded, and I may have over rounded, to be honest with you. So that I suspect that's where the difference comes in. It's probably an issue of just me rounding. If it's
I did it again. I still came up with the same thing. So
okay, yeah, I think that there's it's an issue of rounding, and so yeah, I think, yeah, but that's the correct equation for sure. Okay, Nathaniel.
Okay, thank
And then, so now it asks for, we got the equilibrium constant, so we can check that off. Now we're going to do the free energy change, standard free energy change. All right, so going back to our relationships that we just learned about, delta G0 is equal to minus NF E0 cell, right? All right, so our NFE0 cell was roughly 1.25, and I think that's where I'm looking now. I think the number here 1.3 actually came from an E cell of 1.247. So that's the difference, Nathaniel. Your number is indeed correct. Mine's wrong. Okay, so that's going to be equal to two. Let me do this since I'm gonna get rid of some stuff here because I do want to make this really as clear as I can, at least. Let me just get this. We did that number. So so again, it's going to be, move over here a little bit. It's going to be a minus sign, and then 2, n is 2 times 96,487, or what was 85 is what the book uses. I'll do that. I'm hardwired to 96,487 because that's what I learned when I was in your shoes. Okay, 96,485 joules per mole K, right? Times the cell voltage was, and I'm going to be more accurate that way. It will be more right. I think it's 1.247 volts. Okay, and that equals minus 240.6 kilojoules per mole. So indeed, delta G is negative, very thermodynamically favored, and 240 kilojoules per mole relates to that huge KEQ of something to the power of 10 to the 42, which is a huge reaction. And what does that mean? Let me ask you, do you think that silver ion would be corrosive to an iron pipe?
Yes.
It would be absolutely, it would eat it to pieces, wouldn't it? Thermodynamically, at least it would. Now, kinetically, yeah, you could probably slow it down, but thermodynamically, your iron pipe would literally dissolve probably right before your eyes because that's so thermodynamically favored. Does everyone understand that concept of corrosion? All corrosion is just oxidation. Corrosion is oxidation. It's taking electrons away from stable metal surfaces, and it causes them to ionize and go in solution. That's all it is.
Dr. Jernigan?
Yes.
Okay, so we had 2 moles of electrons transferring there.
Yes.
But do you not put moles with that too? Because if you did, then you'd cancel out and you'd just have negative
No, you would.
200.6 kilojoules.
I think you do,
so
don't
in
you?
other words, we don't have kilojoules per mole, we just have kilojoules because that would cancel.
I think you're right. Yes, sir. I think you're right. Ooh. Yeah, that's interesting. Is that right?
Because sometimes when we have, multiple moles or something, I'm trying to figure out which one of these, of the reactants or products, are you basing the mole count on? You see what I mean? If you don't just have a certain amount of kilojoules, if you're per mole, which one are you looking at?
Right. Yep. No, I understand. And I believe, well, let me answer one of your questions, because this is one of the ones that Elizabeth raised too, and that is essentially, how do you know what N is? And the reason, and Elizabeth, you had in the example we had earlier, we had one was 3 and one was 2, so it came out to be 6. And in that case, then you'd put in, based on this, and unless someone tells me otherwise, I would put N of 6 there, okay?
Yes, that makes sense.
Yes, I would put an N of 6 there. And part of it is when you go and you plug that in, and the previous example we did where we had KEQ, of course, you're going to have already balanced that equation, and that factor will be represented in the exponents of those corresponding concentrations, if that makes sense. So this just carries it through complete so that you're completely consistent all the way across, okay?
So would N in this case be 3 then, or is it just still 2?
No, N in this case is 2. Again, we're multiplying the silver plus 1 electron going to silver 0. We have to multiply that by 2, right? Because we've got 2 electrons up here. We've got to balance that. We can't go back. We can't divide it. We gotta keep it consistent, and it has to have unit charge, okay? So if there's a 2 or a 3 or whatever, if there was a 3 electrons in the iron, and of course you can do that, you can make an iron 3 plus. If there were 3 electrons, we would have to multiply this equation by 3. But as it is now, it's going to be by 2. Okay. Yeah. Okay. But yeah, that's a head scratcher, Nathaniel. I'm going to have to think about that some more, because I thought that this delta G calculation gave me units of kilojoules per mole, but you bring up an interesting point. Let me look into that, okay?
Okay, and if it does come to kilojoules per mole, I'd like to know per mole of what, and how you know per mole of what you're talking about in your equation.
Yeah, let me
Thank you. Yeah.
let me make a note.
As far as I understood it from the textbook, when you do the electrons, when you plug in N, you plug it without any units. And then your V cancels, so you're left with kilojoules per mole of substance.
It could be that. It could be, and the reason that it's unitless is, let me go back here if I can get let me go back and see what we had here in this. Thought I had a relationship. Thought I had all my calculations somewhere. I'll just send you guys a note offline, okay? But
thank you.
Yeah, I'll send a note to that effect. But I think, unless I find out otherwise, I think Elizabeth is right, is because it's number of electrons per mole or something like that. So in fact, N is unitless. Yeah, that's what you were saying, Elizabeth, right?
That sounds right.
Yeah,
I'd just like to know which one, because you had 2 moles of silver there and 1 mole of iron, so it's like, which one are you looking at?
Yeah, no, that's a great question, and we'll work on that one. Okay, so we talked about, and the only thing here, I'm going to just touch on this because we never have enough time, but sometimes we go back and forth between E cell and E zero cell. The only thing in this easier, we use the superscript 0 in electrochemistry just like we do in the thermodynamics. The 0 thing, all that means is it's a standard condition. There's nothing different about that E. It's just, it gives us a standard condition under which we can, for example, that's where log K is, that's the relationship with K. And what it means is, let me see if I can get to the next one, just so we know. Yeah, the superscript 0 denotes standard conditions. It's 1 atmosphere, it's 1 molar, that kind of thing. And unless you say it says otherwise, it's at 298 K, right? It's at room temperature. When we use She as one of the electrodes, what I mean by She, standard hydrogen electrode, I'm going to show you that in a minute, it becomes the anode or the cathode. Let's see here. Yeah, so in other words, the standard hydrogen electrode, and this goes right back to the initial table that we talked about, all of those standard reduction potentials relate to the standard hydrogen electrode. That's why they have that 0 superscript, okay? But fundamentally, can you have a potential of a copper 2+ copper 0 couple relative to the potential of an iron 0, iron 3 plus couple, yeah, it's just a delta E. It's not, that delta E is just not a standard potential. It's legitimate. It's just not standard. Okay, so for whatever that's worth, it's in a practical world, when you're making batteries or whatever, all you're concerned about is how much voltage you can get anyway, right? Delta E is what really matters. But for having a reference, then you got to have a reference. Okay, let's see. I thought I was going to okay, let's see here. Let's see if we want to work this one or move on. I think we've worked on a fair amount of these.
Dr. Journey,
Yes.
if we have a chance, I would like to look at what happens when they write it out in the cell notation, and then
Yes.
how you know, and give you the concentrations, and then how you know which one is the product and which one is the reactant for putting in your equation with Q.
Yes.
Because sometimes that can get kind of confusing. If they just write it out in standard form, it's easy to see, but it's not always easy to see in cell notation.
I think I have an example on that coming up, but I'll make a note just in case. But yeah, the double or single lines and the positioning left to right, all that kind of stuff. Yeah. That's a convention. And I think we may touch on that. Let's go ahead. We've done these. I think you guys are, I've got some other things in here, and I've got some sampling practice. We've already talked about all this, so I'm just going to move right on here and get on to the next. Okay, so we talked about this, and again, K versus Q, it all depends upon whether or not you're at equilibrium. If you want to drive a reaction, obviously you can't be at equilibrium if you want work, right? If you want to create work. So you would need to adjust so that you're not at equilibrium, because all of these cell reactions will ultimately go to equilibrium, right? These are DC, these are direct current. It's a direct current. Electrochemistry is direct current, right? And so electrons are going to continue to flow based on delta E or the delta G until delta E goes away. And delta E is normally pretty stable because of that log term. But at some point, your battery will reach equilibrium. That's what, in other words, you got a dead battery when you're at equilibrium, right? And you have to go and you have to do some electrolysis to get it back out of equilibrium. Okay, so this is stuff we talked about. Do we want to do this one? This would be one worth doing real quick. And I'm just going to show you this kind of, the cell convention is important, but even more importantly, I think, is what's brought up here in this example. And that is, we've got a concentration cell here. We've got a concentration cell, and it's asking us, it's asking, is the process spontaneous? But in other words, what's the cell? What's the cell voltage? That's really what it's asking us. So the anode on this is going to be, and again, oxidation at the anode, and so it's going to be cobalt. In this case, S is going to cobalt 2, right? It's getting oxidized, plus 2E. And again, lacking a table, what I would look at is the direction. That's what I'd look at, okay? Cobalt solid going to cobalt 2 plus, okay? And then the cathode is going to be iron 2 plus 2 electrons going to iron 0. Okay, and then so E cell, and instead of writing the couple here, I'm gonna write E0 right here for these couples, And this one is going to be minus 0.28 and minus 0.447. Okay, so E cell as written, E cathode minus E anode is equal to, again, I don't want to overuse my C's, is equal to E0 cathode minus E0 anode, and that's equal to minus 0.447 minus a negative 0.28, right? Yeah, minus a negative 0.28, which is a plus. Got two negatives there, so that's a plus. And that comes out to be minus 0.17. Okay. So this reaction is not spontaneous under standard conditions. Okay. It's not as written, it's not spontaneous. You would want to have, if you had cobalt 2, and iron 0, then you would be going the other way, and you'd make it spontaneous. But as written, it's not spontaneous. All right, so
Dr.
that's
Harrigan?
negative. Yes.
Okay, so they give you concentrations there. As long as you figure it out from the half reactions, if it is negative, regardless of concentrations, will it always be non-spontaneous? Like, in other words, is there no way you can change concentrations to make it spontaneous?
The answer is that you can affect concentrations, absolutely. So and that's a perfect lead into the second part of this equation or this problem, because we have just started. What we're going to do now is we're going to get away from the E0 cell and do our E cell, which relates to the log Q. Okay, so Q here, and again, I'm getting a little, but Q is equal to the concentration of cobalt 2 plus, right, over the concentration of iron. And I'm glad you asked that question, Nathaniel, because that's extremely relevant. So cobalt 2 plus is equal to 0.15 molar, 0.15 molar, divided by iron 2 plus is 1.94.
I think maybe I made a mistake, but I think the iron is being reduced, right? So it's the cathode. Cobalt is being oxidized, so it's the anode. And our reaction says we should take our reduction and subtract the oxidation. So shouldn't it be 0.28 minus 0.47?
So if you wanted to make a galvanic cell, then that would be positive, right, Elizabeth? If you did the math that you just did.
Yes.
Yes, but I think the point that they're bringing out here is they want you to solve it as if you're making it go to the right.
Oh, okay.
Yeah, that's the point of this example, and I'll show you another as we proceed here. The point they're trying to make comes out of this concentration question. And just keep this minus 0.17 in mind, which is what we calculated without taking into account the concentrations. But now we're going to take into account the concentrations, okay? And those concentrations are taken into account by using the more generalized version of the Nernst equation, which is E cell is equal to E0 cell minus 0.059 over N, okay? And that is log of Q. So now we're trying to get away from the equilibrium condition with non-unit concentrations. Okay, so with concentrations that are not just at standard concentration conditions. So that guy was negative. Let's go ahead and now take the log of that Q, and I'm going to go ahead and have to cut to the chase here. That actually turns out to be minus E cell minus 0.014 volts. Okay, so this is with concentration. Now, directionally, what happened? We did make it much closer to being positive and therefore spontaneous, but it's still not spontaneous as written, okay? Even with adding the effect of this concentration term, okay? So that's the point of this exercise, is that you absolutely can affect E cell with concentrations, absolutely. And that's why you try to make, that's why you see why are batteries so heavy, right? I mean, you got them loaded up with as high a concentration of ingredients that you can get in there and have it still, you know, be soluble. You really load those things up because you're trying to make that cell last as long as possible, and you do affect it with concentration. So is that clear to folks? Yeah.
Yes. So in other words, on this one, if we were to increase the concentration of copper 2 plus enough and decrease the concentration of cobalt 2, then it would eventually become spontaneous. Because your log would become negative, which would make the positive because you're subtracting.
That's exactly right. You absolutely can do that if you can load it up enough with the right amount of your oxidizing species, or yeah, exactly. Okay. So yeah, that's a more general version of the Nernst equation that takes into account the fact that we often are dealing with Q and not K, and when we're actually trying to create thermodynamic cells that have a positive and favored voltage, we want to make them as favored as we can. Okay, it's 10:40. I'm going to go ahead, and here's what I'm going to do, just so you know. I'm going to work some of these problems out offline, and I will post some of the solutions to them in Moodle. And this is really the last part of the electrochemistry section. Anyway, I'm going to skip on to this. We do, and I got 5 minutes, and I'll get up to a point of working a problem, and then I'll work the problems for you guys offline, and you can continue working additional problems for practice in that sapling series I've got set up. So for redox reactions, it can be difficult to know what species was oxidized and what was reduced. In fact, you know, that's some of the questions that we just been having, right? It is a little challenging, particularly if you're looking on an atomistic basis, and you know which atom in a molecule is actually getting oxidized, you know, and what's the charge. So we have to use oxidation numbers. Oxidation's numbers are inherent to of course, the electron configuration, if you will, the tendency of atoms and molecules to gain or lose electrons, but they may not correspond to ion charges, okay? They may not correspond to ion charges in this case, and you will see why. Here are some rules that we're going to use, and where this is heading, folks, and again, this is what I'll show you offline with a YouTube video, but we're trying to get to a point of understanding how to balance redox equations. That's where we're headed. And in order to balance redox equations, we need to understand some of these rules, okay? And rule number one, oxidation number of an element in an elementary substance is 0. All of those things are 0. Iron, silver, chromium, blah, 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 blah. Everything has an oxidation number 0 in its elementary state, okay? Rule number one. Rule number two, the oxidation of an element in a monatomic ion is equal to the charge of an ion. And what that means, say sodium. Sodium is always +1 in an ionic sense. Once you make sodium ion, it's always +1. And that's, you can look at the periodic chart, right? And anything around that's in the same column as sodium is going to have a +1 charge. Likewise, calcium is +2, isn't it? And so, you know, these are some common rules that relate to the periodic chart of the elements. certain elements have the same oxidation number in most compounds. You know, group 1 metals, I just mentioned sodium +1, group 2 +2, that's your calcium metals, right? And then fluorine is always -1. You just simply cannot oxidize fluorine. You can get it to 0 in its elementary state, but fluorine just is so electronegative. It doesn't oxidize, okay, other than to 0.
Well, Connor, did you get your work done?
Did someone ask a question? Okay, so yeah, so that's fluorine. Oxygen is normally -2. It's not always. Oxygen is one of those. Peroxide is -1, okay? But typically oxygen is -2. And nitrogen is usually -3, etc. Hydrogen is normally +1, of course. And in rare cases, you'll see a -1, but not in electrochemistry that I'm aware of. And you got to look at the periodic table. So this goes back to Chem 1 and your guys, you know, looking at the configuration of those valence, you know, those Lewis acid structures and that valence electron structure. You sum the oxidation numbers of all atoms to equal the charge of the molecule, and that's where it comes up. So with that in mind, the following guidelines in this section of the text are to assign. We want to use those guidelines we just talked about, and then this will be our last slide, to assign oxidation numbers to all the elements in the following species. So hydrogen sulfide, what's the hydrogen? +1, right? There's 2 of them, so that's a total charge of +2. And sulfur is therefore -2, right? Because we're given rules around, we're given a rule around hydrogen, so we can use it. So hydrogen is 1 plus times, there's 2 of them, equals 2 plus. Therefore, this by definition, since the whole molecule is 0, right, it has a 0 charge, S is going to be -2. Does everyone see that? Let's do sulfate, SO3 minus. Sulfate. Okay, so oxygen, -2. We have 3 of them. 3 times -2 equals -6. Okay. We have a net charge of -2, so we got to get a 4 out of sulfur, right? We got 1 sulfur, so we're going to have to get, so it's the sulfur by difference, since we have to end up with -2, the sulfur is going to be equal to +4, and that gives us the -2. Okay, everyone see that? Okay, good. And then let me do the last one, and then we'll finish the sodium sulfate. As we mentioned, sodium is Na is +1, right? So you got 2 of them. So you have two plus charges. Sulfate, the total sulfate we know now, since that's a neutral molecule, that's got to have a -2 there, right? So we've got 4 oxygens. So it's oxygen is 4 times -2 equals -8. And then sulfur is we have 1 times some number. X is going to have to give us by when we add it to the oxygen, it's going to give us a 0 charge, right? So sulfur is going to be 1 times, did I get that? No, it's got a -2 charge. I'm sorry, the sulfate has a -2. Getting ahead of myself. Yeah, the sulfate has a -2 to balance the 2 sodiums. So that's got to be a -2. So in order to get a -2, -8 plus, let's see if I got that right, +6. Yeah, it's going to give +6. -8 plus 6 gives us -2. And that -2 combines with that +2 to make it neutral. Okay. So folks, we're out of time. Thank you all. You guys have been super troops for the semester, and gosh, it's been just an immense pleasure on my behalf anyway to be here and be a part of all this. You're gonna be finishing up soon. You can take some well-deserved break time. But meantime, I will be doing some, as I said, I will be doing some work to finish this chapter up and post it, number one. And then number two, I will plan a session on Wednesday to review some of these other questions that folks have been sending my way. And I'll send out an invitation. You'll be welcome to join me for that Zoom meeting, but regardless, I will also record it. Okay?
Thank you.
All right, guys. Good luck, and we will see you next year. At least some of you, most of you. All right, have a good one. Bye now.
Thank you.